Hi everyone, welcome back to the second video lecture on heat treatment for steel part 2. In this video lecture, we are covering some remaining heat treatment process such as hardening, tempering, Austempering and Martempering. Okay, these are the few important heat treatment carried out for the steel to obtain the desired mechanical properties. Okay, we will start with the hardening heat treatment. The hardening heat treatment is mainly depends upon the heating the predetermined temperature. I will show the temperature for the hypo-Eutectoid steel and the hyper-Eutectoid steel is a different range of temperature as in the case of that of the full annealing process. After heating, we are rapidly cooling to a room temperature with the help of a water or oil or salt water. So why we are need to get this rapid cooling? So what should be the cooling rate such that we have to get the desired mechanical properties? The cooling rate should be equal or more than that of the upper cooling rate, which results in the non-equilibrium products. Here, cooling rate is very important because we need to get the non-equilibrium products such as Martins. We need to get this Martensitic non-equilibrium product. This one. So I will explain with the help of a TTT diagram. I think this I have shown previously in one of the slide that this is a cooling rate. Okay, if it is touching to this one, this is a critical cooling rate. This is a minimum cooling rate where we can get the non-equilibrium products. Below this one, that means the more cooling rate. Like this. So below this one, we can get the non-equilibrium product very easily. When we are getting into the this C-shaped curve, this will result in the formation of paralytic structure along with the martensite, which will result in the softening of the material due to the paralytic region, paralytic microstructure. Because of this one, if you need to get the more quantity of the martensite, we have to cool more than that of the critical cooling rate or equal to critical cooling rate. There, here, so why it is been giving a more mechanical properties because of the phase transformation. Phase transformation is from the austenite to the martensitic structure. Some of the applications demands for the high tensile strength and high hardness value compared to that of the other materials. Hence, we need to get the martensitic structure to enhance its mechanical properties. So, high hardness developed by this process also improves the wear resistance property, which is the sole aim of this process component such as gears, shafts and bearings, where we need to get the more wear resistance property there because they are under the services for the longer duration of time with the different fatigue loading. So we need to get the more improved wear resistance property where you will get only the we can achieve this aim only by hardening heat treatment process. So these 2 points I will explain with the help of a graph. So this is the graph. Because of there in the previous slide there is no space to incorporate this graph, so I have incorporated in the next slides. So here it is hardness, full annealing and hardness. This is the temperature. This is the temperature. Wait, I will give a different color so that okay. So for full annealing, hardening heating temperature. So it is similarly in the case of that of the full annealing. So full annealing as well as hardening heating temperature are both are same. So as I have mentioned, this is hypo and this is hyper, right? For the hypo steel, we are heating just above the A3 temperature, whereas for the hyper steel, we are heating in between. So we can heat for the hardening treatment. We can heat in between the ACMS temperature as well as A1 temperature. So what is the requirement of heating? Why these hypo-Eutectoid steels are not heated here as in the case of that of the hyper-Eutectoid steel? Yeah. So this is the basic question that we can answer with by seeing this graph only. So this is wrong. Why? So if we heat the hypo-Eutectoid steel above the A1 temperature, here we will get austenite as well as pro-Eutectoid alpha. The microstructure will looks like this is pro-Eutectoid alpha, whereas this matrix is gamma. So when we are suddenly cooling, suddenly if we cool this one, this austenite will convert into the martensite, but this pro-Eutectoid alpha will remains as usual. After cooling, so we will get it as pro-Eutectoid alpha along with martensite. Our aim is to get the most we want to get the material with the highest hardness value, because of the presence of this alpha ferrite in the microstructure along with the martensite results in the reduction in the hardness value. So the aim of our increasing the hardness or the wear resistance was destroyed due to the presence of this alpha ferrite. So hence we should not heat the hyper-Eutectoid steel just above the A1. Instead of that one, we are heating above the A3 line, where you can get the completely austenitic phase. From there you will get so austenitic phase. From there cooling, sudden cooling, you will get a complete martensitic structure. So this is the our design. We will fill it will fulfill our desired mechanical property, which is having high hardness value, high wear resistance, etc. Okay, so next is for hyper eutectoid steel, we are heating. So for the hyper eutectoid steel, we are heating just above the, in between the upper critical temperature and the lower critical temperature. That is ACMS line and the A1 line, right? So if we are heating in between these two, by sudden cooling, for example, if we heat here at, so above A1, just above A1, we will have the cemented particle Fe3C and the gamma. So when we are cooling, this will result in the martensite and Fe3C. Correct? Okay. But here is total different case. So we are getting Fe3C and the martensite. As we know this Fe3C is having the higher hardness as compared to that of the martensitic structure. So it will, instead of reducing its hardness value, it will increases the overall hardness of the component more than that of the only getting the martensite, as compared to the that of the only getting the martensite. So heating just above the A1 temperature and below the ACMS temperature, we will get the more harder substance as compared to that of the only martensitic structure, because of this presence of Fe3C in the matrix of martensite. Right? So this is the main purpose and the main difference of the temperature, heating temperature. This will play a very important role, right? And the cooling rate. So cooling rate will also plays a very important role, because we need to get a phase transformation. In previous cases, we are just modifying the microstructures and we are not doing complete phase transformation. Here the non-equilibrium phase transformation we need to get it. So initially it was like austenite to perlite, austenite to protected alpha, everything we are doing with the normal cooling. But here the cooling rate is very important, because we need to get the non-equilibrium phases. Right? So this is the most important two things we need to remember for during the hardness. So next is, what are the factors that it will affect to our hardening process. First of all, chemical composition. So this hardening process are very easy for the alloying elements and the high carbon content elements, that is the hyper eutectoid steel, because it's a very favorable and we can get the desired mechanical properties. This is a chemical composition and the size and the shape of the steel. If, for example, I will explain this one. If the size of the component is this much and the another side, the size of the component is little bigger than here. So when we are doing cooling, so heat will be transferred. There is a heat of the water will be transferred from periphery to the center. Similarly in the case of here. So if it is a bigger sample, the time taken or the cooling, there is a temperature gradient between the surface as well as the center. This will result in the creation of the internal stresses, right? So the outer periphery structures will be transformed into martensitic structure, whereas we are getting very soft ferritic structures at the center. This will result in the internal stresses and this will adversely affect the sample. These are larger substances. Whereas small substances, when we cool this sample, it will transfer all the martensitic structures suddenly, because the heat is transferred suddenly completely, and we can get the martensitic structure and we can get the good mechanical properties with the minimum internal stresses. This is the main difference. This is how the steel size and the shape will affect. Hardening cycle. Hardening cycle means heating rate, cooling rate, as explained here, holding time, everything will affect the final microstructure. The homogeneity and the grain size of the austenite. If there is a non-homogeneous austenite and while we are cooling, that the phase transformation also non-homogeneous, which will result in the irregular shape, irregular microstructures or inhomogeneity in the microstructure, which will result in the adversely affects the mechanical properties. So we need to get the homogeneous and the equiaxed grains of the austenite, and the quenching medium, because it should be more than that of the critical cooling rate CCR, as explained previously. This is a cooling rate. The quenching medium EDA is also affecting this one, and the surface conditions of the steel will also affect the hardening process. This is all about the hardening heat treatment process, from which we can get the more harder substances due to the presence of martensitic structure, which is a non-equilibrium phase product. So next heat treatment is a tempering process. Tempering heat treatment. So as we see from the hardening heat treatment process, we will get the more harder substances and more wear resistant substances, but we are compromising with the ductility and toughness of the material. We lost totally the ductility and the toughness of the material. But to improve this, considering these two property, so to improve this property of improve these mechanical properties, we are doing the post heat treatment process after hardening, that is a tempering process. So heating hardened steels below the lower critical temperature, followed by air cooling or at other desired rates, is known as a tempering process. It is a mainly post heat treatment process. It will lower the hardness and the strength and the wear resistance marginally, but it will increases the ductility and the toughness, impact strength drastically, and so some of the particles, some of the things will be regained. So, some of the mechanical properties will be regained, so that we can use it in the many applications. Here, the product will have the both high hardness value plus ductile, so that we can use it in many applications. So higher the temperature, more is the restoring of the ductility and the toughness. The tempering temperature will play an important role. It is directly proportional. Temperature is directly proportional to the ductility and the toughness of the material. The proper tempering process, tempering heat treatment, will result in the optimal combinations of the mechanical properties, both hardness as well as the ductility. There is an optimum. There is no drastic reduction in the hardness value or drastic increase in the ductility value due to this process. There is an optimum. So desired mechanical properties we will get in the for the most of the things. So hardening followed by a tempering is only the conventional heat treatment process suitable for the improvement in the elastic limit of the steels. Okay, this is the main advantage of the tempering process. The tempering process can be carried out in the totally four different stages. So in another video, I'll make a total different video for the stages that we need to carry out this tempering process. So again, I will draw the TTT diagram. These stages are divided into on the basis of temperatures. At lower temperature, about 200 to 300 degrees Celsius, and about 600 degrees Celsius, about 800 to 900 degrees Celsius, about 1000 degrees Celsius, or something else. I'm not remembering the temperatures exactly. So on the basis of this one, they are divided into 3 to 4 stages of tempering. So that we can get the different tempering microstructures. So I will explain these stages in the next separate video. So next a heat treatment process is Austempering process. So this is the heat treatment process. So where we will get the binetic structure. Binetic structures is a special kind of a structure, microstructure, where we will get only by this Austempering process. So in which we are heating the sample in the austenitic region and transformed, and they are cooled in such a way that we can get the binetic structure. So I will explain this whole heat treatment process. First of all, this is a time temperature transformation diagram. There is a TTT diagram, and this is C-shaped curve, and it is having two peaks. So usually I used to show only one C shape, which is having only, it's not containing any alloying element. Here it contains an alloying element, so that we can get the binetic structures. There are two cooling curves. This is a cooling process is a very important. We are heating the sample in the austenitic region, right? Austenitic region. After that, the cooling process is plays an important role to get the binetic structure. So first of all, it is having two curves here. This is for center and this is for surface. The sample is there. First, this is center region, and the cooling rate at the surface is totally different from that of the center. So it is having two different curves, and they are cooled up to just above the MS. This martensitic start temperature. This is a martensitic start temperature. We are just cooling up to the above martensitic start temperature and holding at this temperature, holding for the long some duration of time, so that all the microstructures which is in the so that we can get the all the microstructure transformed to the magnetic structure, and then it is cooled with a normal cooling, so that the final microstructure consisting of a complete magnetic structure. So this is overall cooling rate for the Austempering process, where we will get the magnetic structure. So this magnetic structure results in the so as compared to that of the hardening and as well as the tempering treatment process, results in the better ductility and the high hardness value and improved impact and fatigue strength for a magnetic structure. But only one disadvantage is we need to maintain this cooling rate, critical cooling. This cooling rate is very crucial. So if you enter little bit into this martensitic, enter into this martensitic start temperature, already the martensites are started forming, and again we will get a here martensite plus bayonet we will get. So if you extend this curve up to here within this martensite start temperature as well as martensitic finish temperature, so if you hold it at this temperature and again if you cool it, you will get martensite plus magnetic structure. We won't get complete magnetic structure here, which is not a Austempering process. So hence the cooling is a critical, crucial stage in the Austempering process. This is all about the Austempering. Then next we are moving into the last is Martempering process. So here also the final microstructure is we are getting is martensitic structure. Martensitic structure. The cooling, the heating and the cooling is shown in the TTT diagram. As similar to case in that of the Austempering process. We have to heat the sample in the austenitic region first of all. So when we are getting the complete homogeneous austenitic structure, we started the cooling by reducing the temperatures up to just above the martensitic start temperature. We are cooling with a two different curve. This is showing surface, this is center, and this is for the surface. The surface is having the more cooling as compared to that of the higher cooling rate as compared to that of the center. That's why it is at here and here it is showing a little bit higher cooling rate. Sorry, lower cooling rate for the center. So we have to cool up to just above the martensitic start temperature. After here is a different process as compared to that of the austenitic temperature. In Austempering process, what we will do is we are holding this temperature, at this temperature holding for some duration of time, so that we need to get the magnetic structure in the Austempering process. But in the Martempering process, we need to get a bath or the quenching medium such that the rate of cooling should be very slow, that it should pass over the martensitic start temperature and finish temperature to get the martensitic structure completely. Here, so we will get the uniform martensitic structure with the help of a Martempering process. So this is slow cooling rate. That's why we'll get a martensitic structure. Again, we have this is shown. This is shown because this martensite is having a harder, and this will result in the inducing the internal stresses. To remove this one internal stresses as well as to reduce a little bit of the hardness property, so we are doing the tempering process to get the desired mechanical property. This is a tempered martensite. Here we will get. The martensitic results in the minimum internal stresses, reduces the tendency towards the destruction of the cracking, and improves the mechanical properties as compared to that of the tempering process and the quenching tempering process as a tempering heat treatment process. Only by the tempering heat treatment process. The alloy steels are best suited for this heat treatment process. So any steel which can be hardened by the oil quenching can be tempered successfully, because we can this cooling rate is the most important part in the tempering process, so that we can get the uniform transformation to the martensitic structure from the austenitic to the martensitic structure. That's why. So this is oil quenching is a most important thing, where we are maintaining about 180 to 200 degrees Celsius. This smart tempering process will use a better mechanical properties or improve mechanical properties as compared to that of the hardening plus tempering process. But it will is also cost effective. Cost effective to get a martensitic structure. That's why, so most of the people will use the tempering process for the this process, but it's a very crucial process where we need to maintain the cooling rate. Okay, this is all about the tempering. So this is complete heat treatment process for the steel. First, summary. First, we have seen stress relieving annealing. Second, annealing heat treatment, where we have seen different annealing process such as full annealing, partial annealing, subcritical annealing, and recrystallization annealing, partial annealing. Different kind of heat treatment we have seen, annealing heat treatment. After that, we have get into the periodization heat treatment. Periodization heat treatment. Fourth, we have seen normalizing. Fifth, hardening. Sixth, tempering. Seventh, Austempering. Eighth, Martempering. Okay, I have covered almost all type of heat treatment process in this video lecture series for the steel. Only I have covered for the steel. Okay, you will get most of the questions in the competitive exams as well as in many interviews. This is the most important basic questions they will ask for the this annealing heat treatment as well as normalizing heat treatment, this tempering process. In some few cases they will ask for tempering, Austempering and Martempering process. So in my PhD interview, so one of the question I got is based on size of the sample. So if there is an two different sizes samples are given to you, this is a question. I if I remember, this is a question. If I given two different size of the sample, if I do want to do the hardening process, which one we will get a better mechanical properties throughout the sample? I think this is I have answered in the video lecture. This kind of questions will be asked in the interviews. Okay, thank you.